Okay, question number 3.8. A half ring of radius r equals to 20 centimeter is uniformly charged with the total charge Q equals to 0.70 nanocoulomb. Find the magnitude of electric field strength at the curvature center of this half ring. Okay, so in this case, we have a half ring. Okay, let me draw it here. It is a semicircular ring. And the radius of this ring is given r, and we have to find out electric field at center of this curvature. Okay, so because the entire charge is distributed over the length, so we can find out charge density. Let's take linear charge density lambda, that is equals to total charge divided by length of this ring. Okay, so it is half ring, so it is Q over pi into r. Now see, if we'll take a very small segment at an angle theta, which is subtending an angle d theta at center, then this component length would be equals to r into d theta if radius is r. As we know that angle is equals to arc over radius. Okay, so if length of this arc is r into d theta and charge per unit length is lambda, so from here we can write that the charge of this small segment is equals to lambda into r into d theta. Okay, so it will act like a point charge. Okay, and due to effect of this, there will be an electric field away from the charge. We are taking this polarity positive. Let's take electric field as dE. Okay, so this will also subtend an angle theta because these are alternate angles. So this dE will have two components. One is d cos theta, another is d sin theta. Now see, whenever you get a situation which is symmetric about a point or a line, then either you can perform two integrations by taking a component here, or by simple analysis you can see that as we move from this end to this end, the vertical component, this d sin theta, would change its direction. That for first half it is downward, and for second half this component will be upward. So the sine component will cancel each other due to symmetry. Okay, so here we can write a remark that due to symmetry, dE sin theta component are cancelled. Okay, it means the net electric field what we are going to get is changing with respect to dE cos theta. Okay, now electric field due to a small point charge is equals to, we already know the expression that E is equals to K Q over R square. In this case it is dQ, that's why we are writing dE. So we can write here that dE net is equals to K into dQ over R square, where distance is R, into cos theta. Okay, we can replace value of dQ from here. So our dE net is equals to K into lambda into R over R square into cos theta into d theta, as we replace dQ by lambda R d theta. So one R would get cancelled, and if we'll integrate this, then net electric field is equals to K into lambda over R into integration from cos theta d theta. Okay, now see, this theta is angle subtended by the line joining to this component from the horizontal. So if you move in upper direction, then the range is pi by 2. If we'll move in lower half portion, then angle is minus pi by 2. So from here we can write, to cover this entire length, our angle is changing from minus pi by 2 to pi by 2. Okay. So the integration of cos theta is sin theta, and sin pi by 2 minus, okay, let me write that k into lambda over r is into sin pi by 2 minus sin of minus pi by 2. Okay. So sin pi by 2 is 1, sin of minus pi by 2 is minus 1, minus 1 minus 1 minus minus of 1 is equals to 2. So we'll get electric field 2k lambda over r. Okay. So now we can replace, substitute their respective values. That k is 2 into 9 into 10 to power 9. Lambda is q upon pi r. Okay. So q is 0.7 nanocoulomb. So 0.7 into 10 to power minus 9 over pi is 3.14. And we'll get r square if we'll substitute q over pi r, and r is 20, so 20 into 10 to power minus 2 whole square, because it was 20 centimeter. So from here we'll get the E net is equals to 0.10 kilovolt per meter, as we'll get the answer that 100 volt per meter, or we can write 0.10 kilovolt per meter net electric field at center.